Sorry for the technical problem. So our next speaker is Valentina Brosco. She will be telling us more about quantum devices based on twisted Cuprate heterostructures.
So, first of all, I would like to thank the organizer for inviting me to this very nice and interesting conference and giving me the opportunity to present my work. Someone else the microphone. Okay. No. Okay. So let me go straight to the topic. Okay. So yeah, one of the ultimate goal of quantum computing is to build a quantum internet, namely a complex infrastructure capable of processing, storing, and transferring quantum information. The quantum internet is essentially a complex network where sensors, memories, and quantum communication systems will be integrated. Okay, so it's a very let's say, inhomogeneous network with prone to different disturbances, such as, let's say, the coherence losses, thermal effect, where different technologies working in different frequency range, let's say, need to be coupled. And where do superconducting circuits enter in on this game? Well, in many different ways. First of all, they can be sensors. They can be processors, of course, as we have heard in these days, and simulators. What is for sure is that what we understood is that they operate at microwave frequencies. And they can be also transducers. Namely, they can transfer information they can be used to transfer information from one platform, say photons, to another platform based on solid states or spins. So just today I will talk about qubit, but keep in mind this broad view, okay? Because in my opinion, it's a strong motivation to keep looking for different systems and different materials. Okay, so maybe it's not needed, but just to fix the notation, since I'm a theorist. Superconducting qubits are a superconducting circuit, an electronic circuit, and as such, they are made of capacitors, inductor, and a special circuit element that is the Josephson junction. Namely, the Josephson junction is just made of two superconducting leads separated by thin insulating barrier. And the Hamiltonian of this element is made of two terms, and consequently, it depends on two energy scales, the charging energy, EC, and the Josephson energy, EJ. This in the simplest case. Okay? And depend on two variables, n and phi, where n is that represents respectively the charge imbalance and the phase difference across the junction. And the crucial thing about this circuit element is that it gives rise to a nonlinear potential. It therefore allows to encode the qubit by selecting a well-defined transition frequency that we call omega 01. But so naturally, the system enable say, the engineering of the spectrum and of the Hamiltonian by adding different, let's say, different circuit elements, okay, capacitance, different capacitor, more junction, or changing the value of tuning the value of VC or L. Okay, but we do not have to. We have to. We cannot forget that this system is a many-body system. Namely, the Josephson junction, let's say, is N and phi describe the ground state of many interacting systems. So, so actually, I mean, this is not just, let's say, it's a very complicated, is many body nature exploited to control the property of the qubit. Many body effect emerge in particular when we look at fluctuation, as you all know. Fluctuation may be induced by external flows, such as gate voltages or magnetic field, but they may also come from intrinsic sources, for example, quasiparticles, background charges, or magnetic impurities. And once you include fluctuation in the description of your qubit, you end up with an Hamiltonian of this form. Okay, so this is just the qubit, and this is the fluctuating, say, this two essentially. In the simplest case, it's the sum of two terms, this proportional to NZ, that at the end will give rise to dephasing, and the one proportional to Lx that gives rise to relaxation. And due to fluctuation dissipation theorem, in the simplest case of Markovian and weak system noise coupling, you will be able to relate the relaxation and dephasing rate to the spectrum of the fluctuation. So here you will see, I mean, some of the dynamics of the bath and of the properties of your system. Okay, so I hope I've convinced you that difference will be coupled to different sources of fluctuation and different signals. So this can be, of course, used to improve control and coherence, but also enable novel functionalities. And in general, it can be used to probe new interests in physics. Okay, so, and this has motivated over the years a lot of work. And here just an example of a lot of different qubits that have been proposed, starting from the Cooper box that was developed here, and to the going to the flux and phase qubit, and to the plasmon that is somehow related to this Cooper box, and is the commonest qubit used, as you have heard. What is the most important, let's say, why is the plasmon so common and so successful? I think we have already heard from the talk of Nakamura. The crucial point is its simplicity. Okay, the crucial feature of the plasmon is the simplicity. The strength lies in its simplicity. It's just a single junction and the capacitor floating essentially. Okay, no connection. Okay, and this extremely simple design also protects it from external, let's say, noise sources. So its Hamiltonian is just the one that you have just seen before, the sum of the charging contribution and the Josephson energy. And the charging part has this fluctuating term that account both of the coupling to the resonator and the coupling to the noise section. Okay, and the crucial feature is this huge capacitor. So here I'm showing this is the little junction, and this is the huge capacitor in parallel, that essentially absorb the fluctuation and makes the spectrum flat with respect to Ng, that is the gate charge, insensitive to Ng, the level spectrum. So this implies that essentially Nz goes to 0 and completely and exponentially suppress the pure dephasing. So this is the big advantage of this huge capacitor in parallel. Now with my friends and colleague from Dresden, we started to think, can we, use this simple design, this extremely simple design, but with a more complex system material, okay? And the answer was, well, it was given by Nicola, and fabricate very, very high quality junction made of Brosco. That is an ITC superconductor. And the nice thing of this junction is that depending on the relative twist angle of the two Brosco plates, you can essentially strongly suppress the Josephson energy. This means, so this strong dependence of the Josephson energy as cosine to theta on the twist slice go to theta equal close to 45 degrees, the tunneling is dominated by two Cooper pair processes. Okay, this that is usually much smaller than that becomes dominant. Okay, and consider that in this junction the critical current density is extremely high. So even if this is much smaller than this, it's still very large. Okay? Okay. So just let me give you some more detail on this junction. On the microscope image of the junction, where you can appreciate the extreme quality of the interface. And you see that let's say the critical current, this allowed the Nicola Poccia's group to see, I think for the first time clearly, this cosinus to theta dependence. Okay, and many other signatures of this of the fact that transport is dominated by two Cooper pair tunneling processes. Okay, so we started to think in the direction, why don't we integrate one of these wonderful junctions in a transmon architecture? Why is this interesting? Well, it's interesting because, of course, you can maybe make a qubit that has an improved coherence, but it's also interesting because it may be useful to study the physics of this system. Okay, and in general to develop novel quantum derivatives. Okay, so again, this is the same design you have just seen before, but with this twisted junction. We call this hypothetical qubit flowermon because of the peculiar structure of the order parameter at the interface. Okay, and what are the interesting features? So when you have a small twisting angle, you essentially have a transmon, so a single well cos phi potential. But when you increase the twisting angle, these terms start to become dominant, and the system develops a double well potential. Okay, it becomes double well. So effectively, you are kind of engineering your spectrum by engineering your many body wave function. So not anymore. So I'm engineering the spectrum through material design. Okay, and essentially I have a critical angle above which I have this double well, and below which I have just the plasmon, okay? And this critical angle depends on the ratio between the Josephson energy at zero twist and the 2 Cooper per tunneling energy, okay? Okay, now how does the spectrum look like? So this is the spectrum of the plasmon. It's essentially quasi-harmonic, okay? This one, low twisting angle. But when we increase the twisting angle, the potential starts to have these 2 classically degenerate minima, okay? And the spectrum, so to these 2 classically degenerate minima, correspond to essentially classically degenerate ground state. And quantum mechanically, to these 2 classically degenerate ground states, it corresponds to quasi-degenerate doublet. Because of course there is still quantum tunneling that covers them. Okay? So if you look at the spectrum as a function of the twisting angle, you see that when you go to close to 45 degrees, you have a, let's say, exponentially suppressed level splitting between the first 2 levels. But what is more interesting is the structure of the level. Okay. So essentially, if you look at the structure of the level here in the charge basis. So as you increase the twisting angle, the 2 Cooper per tunneling start to become dominating. Okay, is the dominating tunneling mechanism. And at some point, even and odd Cooper per number states are completely decoupled. Okay? So the ground state has only even Cooper per number state, while the first excited state has only odd Cooper per number state. What does this mean for the coherence? It means that there is any it means that any perturbation that is local in the chart will not couple these 2 states. Okay? So while in the plasmon we were seeing also relaxation, because we are still in the plasmon regime. Okay, we still have this large capacitor in parallel. But here we also are we have killed this matrix element of the charge that in the plasmon was coupling the ground and the first excited level. Okay, and well, so this means that also both dephasing and relaxation in this system will be exponentially suppressed. This is the big strength. So it's the big strength of this proposal, I would say. So this means that we can make a sort of diagram plotting as a function of Ej over Ec and theta, the dephasing and relaxation rate. And you see that, so the Cooper per box, okay, the Cooper per box was here. So essentially you had a large dephasing and a relatively small relaxation. The plasmon is here. So you have still finite relaxation, but exponentially small dephasing, and the flowermon is in this region. Okay? So you see that this matrix element N01, that is the one that leads to relaxation, is exponentially suppressed already at a relatively small twisting angle. Consider that in the experiment they can control the twisting angle with a precision of 0.1 degree. Okay? Okay, so of course you can still, if you avoid going exactly to 45 degrees, you can still control your system by using transition to the higher level that are still coupled. Okay, so you can make only the first doublet really degenerate. So there is an optimal working regime where you still have the capability to control the system without. But of course, another question that now arises is the wave nature of the gap particle. Okay, this is of course a very good question, because a standard S-wave junction quasi-particle is suppressed due to the presence of a gap, of a finite gap everywhere. While in D wave, we all know that the gap has nodes, okay, and there quasi-particles are excited at any temperature. So we calculated by using infinite theory, the relaxation that depends on the tunneling matrix element, TKP, on the gap that now is K-dependent, and on the energy of the Vool and V quasi-particle, okay, of course on the temperature. And what you see is essentially that when this TKP is such that at the interface the momentum is conserved, so the interface is sufficiently clean, okay. Also quasi-particle are suppressed because essentially you are putting the node where there is the node of one gap where there is the maximum of the other. And if you conserve momentum, you still have a gap behavior. And if you calculate numerically this integral, this is what you get. So essentially, you see that your quasi-particle rate also decays exponentially with the gap, and it has an exponential dependence on the twist angle that we fitted with this function. It depends on exp sinus 2 theta squared. So at theta close to 45 degrees, and at our optimal working point, it will be exponentially suppressed. Okay, good. Now the question, I guess, is all this feasible? I mean, well, the answer is, of course, I don't know. I mean, I'm not an expert. First of all, I can say that they are working a lot, very hard, to make this junction stable and scalable, using, for example, silicon nitride membrane to protect the junction so that they are stable for months, okay? Which is something not obvious for this kind of junction. I can say that they are already tried to Uri and Nicola. They already coupled a thin visco layer to a superconducting resonator, and they verified that the quality factor is not that much worse, which is, these are extremely difficult experiments, okay? So it's extremely challenging, and a lot of the physics of the cuprates is still not well understood, I would say, okay? Okay, so then we feel like, you know, we have solved this problem of feasible or not, and we go to more complex circuit, multi-junction, okay? And good. So the first thing to think, we started to think in the direction is can we make this circuit tunable, okay? So we started to analyze just a two twisted junction circuit. In this system, essentially, we have the same physics as before, that is controlled by the ratio between the single Cooper per tunneling and the 2 Cooper per tunneling. Okay, but the crucial thing is that now these two terms depend differently on the external flux. Okay, just because they have a different Aharonov bomb interference pattern. Okay, so this implies that there are different regimes. So we call this ratio between the single Cooper per tunneling and 2 Cooper per tunneling Y. Okay, now it depends on the angle, on the twisting angle, and on the external flux. So you see that when Y is larger than 1, we are in the flowermon situation. Okay, so the general doublet to minima and so on. If we increase the flux, this decreases faster than that, and so you kill the double well, and you end up with a single well, plasmon bed. Okay, you increase further the flux, and a second well appears But now it's a pi. So this was this were at minus pi r plus pi r. This at 0, as in the usual transform. A second well appear at pi, but it has a slightly higher energy. In general, is at higher energy. This is true as long as you arrive to phi x equal pi r, where you have exactly the generate well as at the beginning. Okay, and then you may wonder, okay, so good. So both regimes are fine, but let's look to understand better the physics in this different regime at the structure of the states. Okay, so here in the flowermon, you have the ground that is symmetric and the first excited state that is anti-symmetric, analogously to the transmon. Okay, then then you start to increase the flux, you go to the transmon, same, okay. Then you increase further the flux, a second well appear, nothing happens because the states are still confined in the first well. You increase more the flux, and now the first excited state moves to the second well, because this goes down and the first excited state becomes this. In this situation, the two states have the same symmetry under phi minus phi. Okay? And this means that they are completely decoupled by symmetry, not by localization. They cannot be coupled by an anti-symmetric operator like the charge. Okay, so here we have the suppression of relaxation due to localization. Here in the transmon, finite relaxation. Here, 0 because of symmetry. Okay, that was quite unexpected. At the beginning, we were a bit puzzled. But then we said, okay, so what is then the difference? Let's analyze a bit better the difference between these two situations. So the situation in which we have the generate well at plus minus pi r, essentially, so different symmetry. And the final situation at phi x equal pi r, where we have the 0 pi well. You see, the two states have exactly the same symmetry, okay, in the plus minus pi as a function of the phase. So what does this mean? This means that when you apply it, so now, as I said, for charge noise is an advantage, but for flux noise is a big disadvantage, as you can see here. So look at the structure of the spectrum. So here the degeneracy is induced by the many-body wave function, by the fact that you have the dominance of 2 Cooper per tunneling and so on. So it's not perturbed by the flux. Doesn't care. Okay, so the system remains degenerate as long as you have the 2 well. Here it's just a single degeneracy point. It's a sort of sweet spot. So even if the charge is completely fixed, also because these two, this is another way of saying that these two states have the same symmetry, and therefore they are coupled by flux noise, but not by charge noise. So this is in some sense the difference between built-in robustness and let's say engineered robustness. So here, as soon as you move from the flux sweet spot, you have a huge relaxation induced by a huge dissipation induced by the flux. And this is not true for the flowermon. For the flowermon, the flowermon with 2 junctions seem to be robust also with respect to the flux. We can then try to make a sort of scheme to let's say to summarize all these different regimes. Okay, so in this regime, the degeneracy is twist-based, given by nature, by the many-body wave function. In this regime, this orange regime is the plasmonic regime, okay, where there is no clear protection. As long as you remain in one well, you still have essentially the same physics and the same coherence properties. Then at some point, your excited state goes into the other well, and you go into this fluxbiased regime, where you are protected against charge noise, but strongly sensitive to flux noise. Okay? Then we started to to ask ourselves, almost, I don't know, how much time do I have? Ah, okay, good. Okay, then we started to ask ourselves, but what's special of this point? You know, it's strange because the spectrum has a peculiar structure, and we were wondering, is there something strange? Okay, let's look a bit more in detail. So, at the transition here from between the just let me say one thing, that this is not a phase diagram. Okay, meaning it's important to say. This is not a phase diagram because it depends on both the structure of the ground and the excited state. Okay, so it's a qubit decoherence diagram. Okay, so okay, let's look a bit more in detail at the spectrum and the transition between the plasmonic and the flux-biased regime. So essentially, in the plasmonic, we have, as usual, even, odd, where even, odd means even, odd under phi minus phi. Okay, even, odd. The ground state is even, the excited it's odd, and so on. Then, in the flux bias, as we have seen, we have even, odd, even, odd. This is the symmetry structure of the excited level. And the transition point, what happens? It happens that the ground state is even and non-degenerate, but all the in pairs. And this point is actually this structure of the spectrum actually points at a special point. It's called the supersymmetry, a special symmetry of the Hamiltonian, a special structure of the Hamiltonian. That is called supersymmetry, like the supersymmetry that you have in high energy. Okay? And what happens when you have supersymmetry? So when you have supersymmetry, your Hamiltonian can be written as the square of the supercharge of a supercharge operator Q, and it commutes with a convolution operator K. Okay? It's just like when these two conditions are satisfied, then the spectrum has this structure. So the first, the ground is non-degenerate, and all the other excited states are degenerate in pairs. These are the supersymmetric partners. Okay, and here in this system, this supersymmetry point divide, let's say, separate two very different, very distinct decoherence regime. So you can, by studying the coherence, you can detect the presence of this type of point. Now, well, the supercharge operator has a strange structure, but okay, the important thing is of course in real system all these calculations were done for identical junction, everything. Well, in an idealized situation, what happens if you have differences or asymmetries between the junctions? Well, the main message here is that essentially you are robust with respect to asymmetry in the size of the junction, J and kappa, but very sensitive to angular asymmetry. So if they have different twist angle, this may lead to problems. In the first case, where you have just zero angular asymmetry, you can still have a certain supersymmetry still preserved up to a certain energy scale. Okay, and of course, this leads to also to less efficient protection in the case in which you have twist angle asymmetry. Good. So essentially, this brings to my conclusion, and I hope that I've shown that there are a lot of some we have seen also in the previous talk of new opportunities for superconducting devices. May come from material design and first improve coherence, but also something I did not discuss, but for sure will be the focus of our next work, novel functionalities that maybe are not possible or not, let's say, with current material. So exploit the material to open novel, let's say, type of coupling, engineer novel type of coupling like nonlinear response or chiral like matter coupling. And then there are also this system a very fundamental question, namely the role of spontaneous symmetry breaking in this system. And for example, one could investigate spontaneous symmetry breaking in the presence of dissipation. And eventually, also I think that this kind of experiment may provide new spectroscopic tools, new tools in general, rather than spectroscopic, to investigate material properties. So with this, I thank you for your attention.
Right, thank you very much, Valentina. Do we have any questions from the audience? Yes.
So thank you very much for the exciting talk. So I have a question. Actually, the topological nature of the twist from junction. So you mentioned that if the twist angle is 45 degrees, so it's host something like Majorana or something like that. So this kind of nature is included in your calculation of the potential profile and also the quasiparticle coherence. So this kind of the nature was taken into account in your calculation?
Yes, I actually have also a slide with that. So essentially, there was a work, a theoretical work, that came before the experimental work, studying the topological properties of this twisted heterostructure. And the point is the following. So if you just calculate the volume of the Jan spectrum and you look at its topological properties, what you see is that in fact at the high twist angle, you is whether ±2 or ±4. So you don't have unpaired Majorana fermions. As far as I understood, I'm not expert on topology. One thing I think is that this is, in my opinion, but as I said, I didn't really impose in the outlook. I didn't really investigate this point, is that this topological gap that opens is the same gap that protects you from quasiparticle tunneling.
Yes.
Okay, but I didn't really connect it the two, let's say, the two viewpoints. Because I mean, condensed matter physicists have a view, and we qubit people have another view, but I think we are saying the same thing.
Okay, but it should be quite interesting.
Yes,
it is, yeah.
I think
okay.
so.
Thank
yes.
you.
Do we have another question? Yes.
Hi, thanks for the talk. I was wondering, because you said this is just a transmon, but an upgraded transmon because it's suppressing relaxation errors as well. Do you actually have numbers for like T1 and T2 for the devices that you end up constructing? Or is it not? It does not yet reflect the theoretical predictions you have because it's not a simple.
Numbers.
Yes.
Yes, we tried to calculate numbers, of course, but okay. What you have to consider is that the density, the critical current density is extremely high. Okay, so at zero twist, you have a critical current density of 0.1 kiloampere per centimeter, which is huge as compared to normal. Because this is an intrinsic junction, okay? So the insulating layer is provided by the bismuth oxide layer. Okay, so it's one atom, two atom insulating layer. Okay, so it's extremely high. This means that your Josephson energy, okay, is of the order of 1 terahertz at zero twist for a relatively small jump. When you twist, it becomes much smaller, but still is on the order of 100 gigahertz. Okay, so you start with a very high Josephson energy. Clearly, the big challenge to realize this kind of qubit is make the junction smaller. That is not easy. Okay, because they can make this wonderful interstate, but they are around 10 microns large. So too large. 4 microns is okay, still okay, but they should go to 1 micron to be in the right range. This is in the paper, there are all the numbers. Concerning the improvement, what you have is that, of course, depending on how close you go to 45, you have an improvement of it scales linearly. The order of magnitude improvement scales linearly with the angle. So if you go more or less to 43 degrees, you have 3 to 7 order of magnitude improvement in the relaxation rate. Okay, so it's huge. The improvement is huge in principle, and still you have control because the higher doublet is not completely suppressed. The transition between the higher doublet.
All right, thank you very much, Valentina. So I think we are done with this session. Maybe we can thank both speakers once again.